And we're back. All right, today we are going to talk about the kinetic molecular theory of gases, which talks about the behavior of individual gas particles. So this kinetic molecular theory, so far we've talked about what happens, how each of these variables are related, pressure, volume, temperature, and amount, number of moles, but we haven't described why they happen. And in order to describe why they occur or why they happen, we make models because we cannot see these individual particles. So as we're going through each of these gas laws, I'm going to show you how they're related. So this first one, the effect of decreasing volume, and we're going to see how pressure is affected by that. So this one is analyzing Boyle's law. So why are volume and pressure inversely related? So if you look at this piston, or it could be a syringe, similar to the lab you did 2 weeks ago, where when you press the syringe, you're decreasing the volume. And now when you decrease the volume, here you are increasing the pressure. And the reason why you're increasing pressure is each of these individual gas particles is hitting the walls of the container more often. So the gas particles are hitting the walls of the container more often. And that's what causes an increasing pressure. And keep in mind that it's constant temperature and a constant amount. The number of moles is constant. So if we look at the ideal gas law, which remember is PV equals nRT, if we arrange that for pressure, so pressure is nRT, and then it's over V, or we can multiply it by inverse volume. So if we think about this, we know this whole part here is constant. Our number of moles is constant, our temperature constant, and R is the universal gas constant. So that's why when you have pressure, it is inversely proportional to volume. And we can do that with the ideal gas law for each of these relationships. So if we look at the next one, we are relating temperature, and we're at constant volume and constant amount. So we are relating temperature to pressure with constant volume and amount and number of moles. So that means we're analyzing Gay-Lussac's law, which we know temperature and pressure are directly related. So when we are increasing temperature, when temperature is increased, that means the speed of each individual particle is increased. Then, since the speed of each individual particle is increased, each of these particles, now, since they're moving faster, they hit the wall more often. So they hit the walls more often, and they hit the wall with more force, with a greater force. So as a result of that, each particle is hitting this wall more often and with greater force. As a result, that increases the pressure. So if we look at the ideal gas law, if we're once again solving for pressure, we can rewrite it. So we can rewrite the ideal gas law, PV is equal to RT. If we want to look at the relationship between pressure and temperature, and everything else is constant, we can look at the fact that nR over V, that part is remaining constant number of moles and volume, times the temperature in Kelvin. So since that part is constant, that shows you that pressure and temperature are directly related. Okay, so now we've covered the relationship between pressure and volume, pressure and temperature, and now we're going to talk about the relationship between temperature and volume. And same thing, the other variables are held constant, so constant pressure and constant amount, or constant number of moles. So here, same thing, we're increasing the temperature, so the speed of each individual particle increases. So same thing, the particles hit wall more often and with more force. And the only way to keep the pressure constant is to increase the volume of this piston, or of this syringe. Okay, so you're increasing the temperature. Each of these individual particles are hitting each of the walls with more force, including the top of the syringe, making the volume of this container increase. So same thing, if we are rearranging the ideal gas law, but now we're solving it for volume. Now we know amount, N, and pressure are held constant, so that makes sense that volume and temperature are directly related, which shows that we're rewriting or proving Charles' law. And now the last one, we've talked about how volume is related to temperature, volume is related to pressure, and now how volume is related to number of moles. So if we increase the number of moles at constant temperature and pressure, how does that affect volume? Okay, so we are explaining here, providing the evidence for Avogadro's law. So if you look here, we are increasing the number of moles of gas. We're adding gas from a new source. So we're increasing the number of moles, or increasing the number of particles. And since here there are more particles, this causes the pressure to increase. Those particles are hitting each other more often, as well as hitting the sides of the container more often as well. However, we are keeping pressure constant, so in order to account for that, we have to increase the volume of the syringe or cylinder. So since there are more particles, each one of them is pushing up on the syringe more than it was before when there was a smaller number of particles. So therefore, the volume will increase, proving that volume and amount, the number of moles, are directly related. So same thing, now we're going to rewrite the ideal gas law once again, but now temperature and pressure are constant times N, so that shows you that moles and volume are directly related. And each time here we're using the ideal gas law. However, even though we are assuming that all of these gases behave ideally, they actually do not behave like an ideal gas the entire time. So keep in mind, this kinetic molecular theory, we're assuming 4 things. So we are first assuming that the particles are so small that the volume of the individual particles is negligible, or 0. So, but we know actual particles, if this is water, or if this is nitrogen, these particles actually take up space. So that's not actually true for what we call real gases. And we know the gases, when they're moving, each particle of a gas, when it's moving around in a container, it's in constant motion. Okay, and we assume that all of the interactions are elastic. Meaning that the individual gas particle, is either hitting the wall and bouncing straight back, or it's colliding with another particle and bouncing right off. However, sometimes the particle is either attracted to the wall, or it's attracted to one of the other particles, intermolecular force. So, therefore, many of the collisions are actually slightly inelastic. Meaning, sometimes they collide and interact with each other for a certain period of time. And relating to that, we assume that the particles exert no forces on each other, meaning we are ignoring intermolecular forces. But for most gases, they at least have some sort of, and most gases are nonpolar molecules, so most gases have dispersion forces. Okay, then the fourth postulate or fourth assumption we make is that the kinetic energy is directly proportional to Kelvin temperature. So that means all gases at the same temperature have the same average kinetic energy. So that means if you have gases at the same temperature, hydrogen, nitrogen, oxygen, they all have the same kinetic energy. So if all three are at STP, they all have the same kinetic energy. And obviously the higher temperature means greater motion, greater velocity. So kinetic energy is directly proportional to temperature, and the relationship is kinetic energy is 3/2 R, the universal gas constant, times the temperature in Kelvin. But all you need to know is the fact that kinetic energy is directly proportional to the Kelvin temperature. Okay, now you can skip ahead to the next section where we're talking about root mean square velocity. Okay, so this is a little different than kinetic energy. At the same temperature, each of those gases has the same kinetic energy. However, that doesn't mean they're traveling at the same speed. So this root mean square velocity, and it's represented by the u, or mu, the cursive u, and then the RMS stands for root mean square velocity. So here we're using a new value of r, which will always be given, and the reason why it has a different numerical value is due to its different units. So for this one, we're using joules per Kelvin times mole. And with a joule, its actual unit is kilograms times meter squared over second squared. So that means, in this equation, so it's the square root of 3 times r times T, so the temperature always has to be in Kelvin. And then the molar mass is the capital M. However, here, since you're using a joule, the molar mass has to be in kilograms per mole. So that these units here will cancel out. So that means left over, our final units, our speed, is in meters per second. So what this means qualitatively is, if you look, molar mass here is in the denominator, is gases with lower masses, with lower molar masses, will travel faster at the same temperature as will gases with higher molar masses. The reason for that, there's more frequent collisions. And this relates to when gases either diffuse or effuse, which are different. So when we're talking about diffusion of gases, we're just simply talking about the mixing of any two gases. Okay. However, effusion, it's a subset of diffusion where it's the gas traveling through a small opening into a larger container. So think about if you put a hole into a balloon. If it's helium in that balloon, the helium will be traveling out of that small opening in the balloon. So the rate of effusion measures the speed at which the gas is transferred to the larger chamber. So the effusion here, so if you pretend that this is a balloon, and this is like helium gas, so it has to travel through this opening, that is inversely proportional to the square root of that molecule's molar mass. So that means helium would diffuse much more quickly than, let's say, neon or argon or krypton gas. Okay, and if we look at the relative rates here, and this is referred to as Graham's law of effusion, the square root of each of these molar masses is equivalent to the rate of each one of them. However, if you look at this equation, it's the rate for fusion of gas 1, and then with the molar masses, it's flipped. So it's the square root of molar mass of gas 1 at the bottom there, then it's the rate of effusion for gas 2, and that's up top in your numerator there. So once again, the less massive gases travel or effuse faster. So for an example here, hydrogen gas would effuse faster than, let's say, fluorine gas because it has a lower molar mass. And what you could do, you can calculate how much faster hydrogen travels than fluorine gas. So if you looked, if this was hydrogen and this was the rate of fluorine, so if you look at the square root of the molar mass of hydrogen, which is 2.02 grams per mole, and then this was F2, the molar mass of F2, 2 times the molar mass of fluorine, so that's 38. We can now calculate how many times faster hydrogen is traveling through that opening than fluorine is. And you'll have, I believe, 1 or 2 of those on your homework problems. Okay, so now we're going to talk about, in terms of these molecules, yes, they take up space, they have volume, and yes, they are attracted to each other. So how do we correct for that? So these are actually real gases. No gas exactly follows the ideal gas law. So we must especially correct for this when pressure is high and temperature is low, meaning if the temperature is low, the molecules are moving slower, and the pressure is high, so volume is low, so there's a higher proportion of volume that these molecules are taking up. Okay? So the concentration is high, they're taking up more space, and since they're closer together, the molecules are much more attracted to each other. So that means gases act more ideally at low pressure and high temperature. So at low pressure and high temperatures, gases act close to ideal gases. Okay, so if you look at this graph, PV over nRT should always equal 1 for every ideal gas. But looking at these actual gases, N2, H2, CO2, CH4, obviously that's not the case. However, for all four of these gases, they act close to ideally just at low pressures. Okay? And they start to deviate more and more the higher the pressure gets. And if you look at this graph at 3 different temperatures, specifically for nitrogen, it's more ideal at higher and higher temperatures. So if you look from 203 to 293 to finally 673, it starts to get closer and closer to 1. So at high temperature, it acts more ideally because at high temperature, the molecules are moving faster, meaning they have less time to interact with each other. They have less time to attract each other. And then the reason why at low pressures they act more ideally is the actual gas molecules are taking up a higher percentage of that volume. So we can account for that in terms of the ideal gas law. So it's with the ideal gas law, we're using the kinetic molecular theory, we're assuming gas particles do not take up any space. However, with this van der Waals equation for real gases, it takes into account the corrected volume, meaning that the actual molecule takes up space. So here, the molecules have finite volumes, meaning that the individual particle takes up space. So that means the volume available in a real gas is actually slightly less than the volume of the container due to the volume taken up by the gas particles. So that's where this correction comes from. Because normally you would see ideal gas law PV just equals nRT, but this volume is slightly reduced due to the fact that the molecules take up some space. And still N is the number of moles, and B is the constant for that particular gas. And same thing with A here, where it's the corrected pressure, and that takes into account the fact for the attraction between individual gas particles. And the reason why we have to take into account the attraction between particles So if you look here, in part A, there's a relatively low concentration. So if there's not very many particles around here, this particle will just hit the wall and bounce right back. So at lower concentrations, at lower pressures, it's not affected by the other molecules around it. However, at higher concentrations, each of these molecules have slight attractions to each other, making this force of this molecule, of this purple molecule, against the wall, slightly less than you otherwise might expect it to be. So when accounting for the attractions between particles, that makes the pressure slightly smaller because those particles hit the wall now with less force. And that decreases and makes the pressure smaller. So that's why we use this A, that's the constant for each gas. N is still number of moles, and V is volume. Okay, and now, for each real gas, that means the actual observed pressure is lower due to these intermolecular reactions. So if we're comparing different gases, we have to look at the intermolecular forces, and usually for gases, we're dealing with nonpolar molecules, which are attracted to each other by dispersion forces. And if you remember dispersion forces, the larger the dispersion force is the result of more electrons, or the larger the molecule. So if we have these following gases, hydrogen, H2, nitrogen, N2, methane, CH4, and carbon dioxide, if we look, if we're going from left to right, the number of electrons increases, meaning, as we're going from left to right here, there's more intermolecular forces, meaning larger dispersion forces. So that means, as we go from left to right, CO2 deviates much more from an ideal gas, it's more of a real gas, than is H2, since two molecules of H2 are less attracted to each other than two molecules of CO2. And it's similar for the actual volume that these take up. H2 has a much smaller volume than CO2. So that's also why hydrogen gas behaves more ideally than CO2 gas. So, for example, here, hydrogen would have a low A value, meaning it's not very attracted to each other, and it would have a low value for B, meaning it takes up a small volume in comparison to that whole container of gas. Okay, so you'll always be provided with these constants. So if you look at H2, in comparison, it has a low A value and a relatively low B value in comparison to all these other gases, because for the low A value, it means it has a low dispersion force attracted to each other, and then for B, it has a relatively small volume. Where if you look for, let's say, water, it has a very high value for A, and that's because water and also NH3, they both have hydrogen bonding. They're very much attracted to each other, so that greatly lowers the pressure. And same thing here, All these molecules at the bottom here are much larger, so they have much larger values of B, meaning they take up more space relative to the size of the container. So a low value of B indicates that the gas is very small, like hydrogen or like helium. And that generally increases with the size of the gas molecule. So a low value for A reflects that the correction must be made for pressure. And low value means weak intermolecular forces, meaning dispersion forces. And a high value, like those for NH3 and H2O, mean that there's large intermolecular forces like hydrogen bonding, and you have to take a much larger effect for pressure. So for your homework, you're going to do a couple calculations where you calculate the pressure using just the ideal gas law, and then also use the pressure using the van der Waals equation. And when rearranging the following equation here, and you're solving for pressure, you have to make the following rearrangement. So you have P equals nRT over V minus NB minus A times N over V squared. So this is why we use the ideal gas law, where if we're just solving for pressure, it's nRT over V, because all this we have to correct for both the volume of the actual molecule and then how it affects the pressure, the fact that those molecules are attracted to each other. All right, that's all for today. See you next time.